Okay, good afternoon, everybody. My name is Asfandyar Kuhi. I'm a multi-product team leader here at Central Innovation. And today topic we are going to look at SolidWorks Premium with predict the permanent deformation on your design, simulate the plastic and hyperelastic material. Let's look at the agenda today. The first bit of this presentation is going to explain why we need simulation. And after that one, we start the first case study with a nonlinear deformation on a ductile material with the case of nonlinear static study. So we understand how we capture the nonlinear deformations. And from that point, when we finish the first case study, we're looking at nonlinear deformation on a hyperelastic material and what are the important figures we have to consider and what sort of formulation we have for hyperelasticity. Again, this would be a nonlinear static case. And at the end, what we are presenting is the benefit of having any FEA simulation and the return of investment. Okay, let's have a look. Looking at the procedure, the traditional procedure, all our, let's say, activities are starting from creating a 3D CAD, building a physical prototype, and bring it to the test performance stage. Well, obviously, if we find any faults, any defects at the test performance, we have to get back and repeat the same procedure, which require a lot of effort, time, resource, and obviously money. Instead, we can suggest and propose a better procedure. If we can do the 3D CAD design, then build a virtual prototype and simulate the performance virtually. Therefore, any early detection of defects, misperformance can be actioned here and simply get back, since the same user can do the modification and there is no physical prototype cost involved, we can validate our model and simply saving the time. In this regard, if you're looking at the traditional serial procedure, what we have is the concept, which is going to either electrical or mechanical design. We go for design validation and technical communication, then it's going to operation. However, if we look at the SolidWorks proposal, we can do all of these activities at the same time and instantaneously update any of this stage if it's required, such as design validation, technical communication, and even data management can happen as a parallel procedure. And this is exactly where we save money, since we are saving time and also resources. With that explanation, we are fully understood why simulation and where it can come to the effect. Now, again, have a look through the licensing, structure we have with FEA simulation in SolidWorks. We are having 3 different levels of software, which is an add-in. You need a base CAD package from us, means SolidWorks CAD. Either it's a standard CAD or even it's a premium CAD. Doesn't really matter. But when you have any of this license, you're able to perform variety of tasks. In a standard, which we previously reviewed this application, we got static studies, linear, fatigue, motion studies, and trend tracker. When you are grading to professional, you can have more and variety of tests here, such as frequency or thermal analysis or even drop test. And at the end, which is the main focus of our topic today, we have SolidWorks Simulation Premium. And specifically today, we are focusing on nonlinearities. However, on top, you can do dynamic loads, nonlinear and dynamic at the same time. And obviously, we have dynamic fatigue analysis, and there is a possibility to look at composite with a multi-layer material stacking on top of each other. With that quick explanation, let's have a quick look about one very fundamental thing. We're talking about elastic and plastic deformation, and we would like to understand what is the procedure in ductile material, such as steel range. So if we look at this graph, this is showing us the stress-strain relation in a different stage of loading in any ductile material. So the first is a linear region, where the stress-strain or force displacement have a linear relation. This is what we explored on our previous study. Linear static, 1 Newton, 1 millimeter, 2 Newton, 2 millimeter. And simply, if you remove the load, everything as a stress or displacement or deformations are removing. After passing one very critical point, which we call it yield, this is where the material is going to show different behavior. So in that case, if we're passing the yield, we will have permanent deformation. And that simply means if you loading up to the yield and pass it, the strain will not return to zero. The shape will have some permanent damage or permanent deformation, let's say, and simply going ahead. If we keep pushing the material, what is happening? The plastic deformation will occur and material will develop some hardening on its surface. It will resist against more deformation until it's reaching our ultimate stress point, and from that point we will see the necking problem and finally coming to fracture. So this is a behavior of any ductile material. As I said, the very good example is steel products. So we have to understand all this procedure. In linear static studies, we are limited up to this region. But in nonlinearities, since this, let's say, relation between force and displacement is going to be changed and it's not in a straight line anymore, it is look like a curve, we need a nonlinear solver and we need variety of, let's say, parameters to represent the material response to the loading after the yield point. So nonlinear static study or even nonlinear dynamic studies are the correct study type to capture such a effect. Now let's have a look about our, let's say, case study. We will have a paper clip and we would like to understand if we're fixing some legs and we're applying even a very small load like 1 Newton, we would like to capture the permanent damage and the permanent deformation on this structure. We obviously, in this case study, we will have a look about two different criteria for plasticity. Nonlinear elastoplastic von Mises criteria and nonlinear elastoplastic Tresca model. All right, this is my design. It's pretty simple. It's a paper clip, and as I said, all SOLIDWORKS simulations are add-in. So you go to the list of add-ins, you activate them, you can set up your analysis here. So starting from new study and selecting the type, again, back to your licensing, nonlinear, static, click OK, and you will have the first study. Just for clarification, guys, what is happening, I've created a variety of study. First, I've started with linear static. And with that one, I would like to understand first if there is any failure happening. Do I need nonlinear or not? You can see I have fixed this one. I applied -1 Newton here. And here is my stress. Yes, obviously I can see there is a permanent damage. And when it's happening like that, then we have no comment what are the final displacements look like, because it's act nonlinearly and the solver needs to be changed to nonlinear. For that reason, you can see I've created a second study. And again, with that one, you can see what are the differences here. I've selected my paperclip material and as ISI 1020. And instead of having linear elastic isotropic model, I've selected von Mises. And what I have to provide for software is saying elastic modulus, Poisson ratio, where is the tensile strength, yield strength, and also a hardening factor after the yield. So these are the inputs you can put in here. All ultimately, if you like, there is a table and curve. You can go and define your stress strain curve. That simply means if I bring this slide back here, we are talking about the reaction, or let's say stress and stress curve from the yield point onward. You have the opportunity to define it. And this is again very important stage. We have to show how the material is reacting against the force after the yield. So simple as putting the information here, we can go ahead with the same definition of fixed 1 Newton of load, and there are a variety of things we can do here. So I've said this is the phase where the load is applying, and this is the direction, and you can see there is a curve here. I can define the loading and unloading phase here. If we consider the total simulation pseudo time as 2 seconds, at 0 seconds there is no force acting. The load is getting 100% applied to 1 second, and it will be unloaded after 1 second. From 1 second to 2 seconds, there is no load. So load and unload. And this is how we can capture the permanent deformation. And this is one of the first and very important differences we got with linear static study and this study, which is nonlinear static. So loading and unloading phases, and obviously you can see in study properties, we have the time increment, how much of the load we are initially apply, and it could go up to what sort of percentage in each iteration when we solving it. And simply there are more advanced, let's say, setting here about the removing of the singularities, convergence tolerance, how many iteration we have to put, and these are more advanced, let's say, setting. If I click on run, what you can see as the first difference is the load is getting applied by percentage. And obviously you can see up to 50% of the load is simply deforming. And after this phase, we go back to unloading phase. So if we want to understand how much permanent deformation, this is the case. We have the unloading phase, and it's simply done. The second difference we can see, you can plot your stress at any time step. 1 is the end of the loading. So this is the stress. Yielded, yes, past the yield point 389. This is the real stress value. I can look at the residual stress if I go to the second stage. So the residual stress here is 125.7 megapascal. So that is how much residual we have. Also, if we're looking at the displacement, that would be the same story. The permanent deformation on here is 6.7. However, at the end of loading phase, it went to 20 millimeter. So the ability of applying this, let's say, stage loading is happening in nonlinear static. Ability to capture the result after the loading phase is another one, and also plotting option and everything else will be the same as you can see in nonlinear. But the main idea is we have some linear material which is passing the yield point and needs to be captured appropriately. Okay, so this is my first case study. In the next case study, what I would like to show you here is the ability of making any hyperelastic material, such as rubber. This rubber, this type of material has no linear region. A rubber is very sensitive to loading, and what is happening, a very small portion of load, it is going to deform very significantly. In this model, we will have a simple tube. We're fixing the end, we're applying 150 megapascal, and we will have a look through what is the case look like. All right, so here it is my case. As you can see, I have created this study, and what I can do instead of any plasticity von Mises, which is not valid for hyperelastic, I have 3 valid models for hyperelastic material. Hyperelastic mono-relevant, hyperelastic Ogden, and in some cases might be viscoelastic. So selecting that one, you can see Poisson ratio is what you can define, and this formulation also needs tables and curves. You can see the test on a simple tension is what I've put as the input here. So I've told the software what is the reaction of load in tension. You have a variety of options. So if you look, you can see there are more curves you can define. Simple tension. Also, we have biaxial here. Okay, let's see. Simple tension, planar tension, and bioaxial tension. What I would like to bring again here is a very important slide information. In any hyperelastic material, we need at least these three, because the reaction of material in a different loading type needs to be fully defined. And this is exactly what we saw in our model. So uniaxial tension, pure shear, and biaxial tension is must to define. And then since we calibrate our base of calculation, we can easily go ahead and solve it. So in this case, you can see I've selected the material as it is. I will go for a high order of the material, apply, close, and looking at this study. Again, as you can see, there are steps of load, material fully defined, and simply we get our result back, which how much stress we have. Again, can go on a different steps of loading, and simply we can understand the displacement on hyperelastic material. We can see the expansion, and we can probe the result at any stage as we want. All right, so two main topics we have covered. How we capture plastic deformation. Yes, we have loading and unloading phase. We have appropriate material model, and we define it at apply material stage. Okay, so this is bringing me to the last topic I would like to cover. Obviously, with any FEA simulation, you have the opportunity to ask us to give you the ROI analysis. We get very few data from you. What is your current activity? How many person are working? If there is any scrap, and we definitely can bring and provide you a full report of total benefits, total investment you've done, when would be the return of, let's say, investment for you in the case of just software purchase, and what is the total benefits onward over the 3 years. Please do not hesitate to give me a call, send me an email for any further technical or commercial information required. Thank you so much for your attending, and we will see you on next session.